This is Breaking Up in Mnesia from Dániel and Onno, and as you may have guessed, this is a talk about a database migration. Database migrations are probably the most overused textbook examples of why to go with software architectures that decouple layers and glue them together with vendor-agnostic libraries, which most probably have the word enterprise somewhere in their name. I believe it's a bit less discussed on why would you actually like to migrate to a new database, and how could you do that after operating for more than a decade without using any kind of ORM software? So let's hope we can still tell you something new and interesting, but let's start with the boring introduction first. We promise to keep it brief and dive right into the interesting part. I am Dániel Szoboszlay. I came from Hungary to Sweden to join Klarna, where I work as a lead engineer, actually for the better part of my Erlang developer career.
Hi, and I'm Onno Vos. I am from the Netherlands, and I'm a senior engineer at Klarna Bank, and I have worked with Erlang for about 5.5 years. So, Klarna was founded in 2005, and it currently hosts a wide range of products, like Buy Now, Pay Later, Klarna Checkout, credit card, bank accounts, a shopping app, and many, many more. Klarna started life with a single monolith called Cred, and Cred is written in Erlang and powered by Mnesia. But by now, Klarna has a very diverse tech stack consisting of hundreds of microservices, but the monolith is still alive and kicking strong. So cool. We now know that you use Erlang and Mnesia, but why, you might be wondering. So let's find out. The choice for using Mnesia was not as deliberate as one would think. It was as simple as that the first developers were keen on using Mnesia, since they themselves used Mnesia in other systems. For 15 years, Mnesia stuck around, and it currently powers Klarna for 8 of its countries. It is worth noting, though, that there have been previous considerations to move to Postgres, but they never made it to production.
And this talk is about breakup in Mnesia, so even though it took us quite far, you could very well guess there were problems too. Let's talk about these issues first. Most of the problems of Mnesia are rooted in its embedded origin. First of all, Mnesia is embedded in the sense that it was famously targeting Ericsson's AXD301 node. In this setup, a distributed database is distributed across 2 boards in a subrack and holds a few megabytes worth of configuration data. A lot of design choices in Mnesia make sense in this environment. Like distribution is AP. If 2 Mnesia nodes would become separated, they both remain operational, but their copies of the data will start to diverge. But this is fine, because the network between the 2 AXD boards is super reliable, so this will never happen. There's not even a real built-in solution for rejoining the separated nodes, apart from picking one as the source of truth and copying over the entire database to the other, which implies the database must be small. This assumption is encoded all over Mnesia. Disk-only copies tables are limited to 2 GB. Disk copies and ROM copies need to fit into your memory. Indexes are generated on the fly when tables are loaded, so large tables with indexes load very, very slowly. And adding or removing columns to a table becomes one transaction that blocks access to the entire table until it transforms every single row. It's not really feasible for large tables. The schema is also hard to change because Mnesia is built around records. During the schema migration, your application must be prepared to deal with both the old and new record formats, which is, as you all know, super inconvenient. But Mnesia is also embedded in the sense that it is a library to be included in your Erlang release, not a standalone service. You cannot install a standalone Mnesia on a server like you could install Postgres or MySQL, and AWS cannot offer you a managed Mnesia service. A library gives you more options to customize it to your needs, but it also leaves a lot of open problems for you to solve, like operational aspects, where to put your log files, what metrics to collect, and so on. Unfortunately, most of these design decisions are the exact opposite of what we need at Klarna. In case of network problems, we would favor consistency. We want to store terabytes of data. We actually want to index those terabytes of data. And over the years, our objects need to be extended without stopping the entire world. Ideally, you would like to use a managed service that is run by a team of experts with safe operational procedures, backups, performance monitoring, all taken care of. And these goals are not impossible to achieve with Mnesia. We have a solution for this. It's called Bring Your Own. We wrote a proprietary CP replication layer. It's called KDB, and it's not open source. First, we were using machines with a lot of memory. At its peak, the database consumed about 1.3 terabytes of RAM, but that's not really feasible to maintain. So then we added the level DB backend to Mnesia, which doesn't have to store all the data in memory. And this library is called Mnesia level DB, and you can find it on GitHub. We implemented indexes as regular tables. Yes, they need to be manually maintained, which we achieve by forcing all code to go through access modules and interacting with the tables. And to avoid changing the schema, instead of adding new fields to the records, we started dumping new data into prop list fields or creating auxiliary tables. And of course, we couldn't outsource managing Mnesia to a cloud provider, but at least we developed our own operational procedures, monitoring tools, backup and restore routines, and they're quite impressive. For example, we can restore a 5 terabyte backup from production into a test environment in about 20 minutes, which is only possible because we own the entire tech stack and can heavily optimize it for a particular use case. However, maintaining all these custom solutions take a lot of effort. We don't get the benefits of being on a large popular platform that is actively developed and where most bugs are found by other people. We are not even on a standard platform within Klarna, where we have DBA teams who develop tooling, take care of compliance, and can generally support you with your problems as long as you use Postgres. Weighing up all this, it became clear that we shall migrate CRED away from Mnesia. Taking a bold decision is one thing, making it happen is another. Let's walk through the major roadblocks on the way to Postgres. The first step is to create a high-level plan for the migration, and the third step is profit, of course. The simplest migration plan one can imagine is the cutover. You set up syncing the data from Mnesia to Postgres. It doesn't have to be synchronous, some lag is absolutely tolerated. Then set up new CRED machines that use Postgres instead of Mnesia. And in the middle of the night, you stop the old CREDs, wait for the sync to transfer the last transaction, and then start the new CREDs. There are two serious problems with this plan. The first one is that Postgres is quite different from Mnesia. It has a different API. It doesn't have an equivalent of every Mnesia feature. And even features that exist in both databases have slightly different semantics. This means a large part of the business logic has to be changed to work with Postgres instead of Mnesia. It's not even a simple find all transactions, replace them with a SQL query like work. I would argue you will have to essentially rewrite the entire application from scratch, which is good because you can make use of all the features of Postgres, but we all know how rewrites from scratch projects tend to fail. It is impossible to even estimate the amount of work. By the time you finish porting existing CRED features, new ones will be written by others. And don't just think about all the new bugs you will introduce along the way. Speaking of bugs, if shiny new CRED on Postgres would have some serious issues, the cutover gives you no way of migrating back to old trustworthy CRED on Mnesia. That would be a similar project on its own. So either of these two problems alone would mean the cutover is a no-go for us. Let's see how could we address them with a better plan. To avoid rewriting all the business logic from scratch, a compatibility layer has to be introduced. It shall present both Mnesia and Postgres behind a common API. Practically, it means Postgres needs to behave exactly like Mnesia. There are only a handful of places where we introduce new API that makes Mnesia behave the Postgres way. For example, we created functions that read or write multiple records to a table at once because it's so much more efficient that way on Postgres, and it's easy to implement it on Mnesia too. The compatibility layer solves the problem of too many changes in the business logic. However, the second problem remains. Switching over to Postgres is still an all or nothing move. You cannot do a safe rollout, first only directing 1% of the traffic to the new nodes and then gradually ramping up if all looks good. And even though the chance of introducing serious bugs in is much smaller in this way, there is still a very likely scenario of running into performance issues in the new database. We don't like bold all or nothing moves. We always want a quick and safe way back. So we had to find an even better solution. We went one step further and not only made Postgres behave like Mnesia from the outside, we also made it part of the same distribution protocol. So the business logic in other nodes would see it's interacting with one single database, even though behind the scans there are two. The benefit is that now you can run Mnesia and Postgres nodes side by side. There is no longer a strict cutover. Bidirectional distribution protocol level compatibility between the two databases was a difficult thing to achieve. Although already using our own in-house replication code across Mnesia nodes helped a lot, but it would have been possible regardless. Like Postgres allows you to integrate with two-phase commit protocols easily. So this is our migration plan. We improved the simple cutover strategy in 2 steps by introducing a common API layer and then cross-database distribution to avoid the 2 major issues, if writing a lot of code from scratch and doing an all-or-nothing switch to the new database. And I'm not going to say this is the best migration possible. One can always find better solutions, but it was good enough, so we stick to it.
Okay, so now we know how to migrate. Well, let's start to dive right into the land of database isolation levels and how we managed to achieve serializability on Postgres without using serializable isolation level. So serializable isolation level is the strictest form of isolation. It emulates serial transaction execution for all committed transactions as if they have been executed serially rather than concurrently. You must be prepared to retry such transactions because serialization errors will happen. So let's take the following example. A hospital keeps track of doctors who are on call, similar to what you might have with Opsgenie or PagerDuty. The rule is that a single doctor must always be on call. And at this point, 2 doctors are on call. And both request to go off call concurrently by first checking the database if the number of doctors who are on call is bigger than or equal to 2. If true, they mark themselves as off call. With serializable isolation level, the first one to commit will succeed, while the second one will fail, as the premise of having at least 1 doctor on call no longer holds true. This example would not hold on the default isolation level of Postgres, which is read committed, but it does hold on Postgres serializable isolation level. So if we take a brief look at Mnesia for a moment, we find that Mnesia uses transactions, which are serializable due to a combination of read and write logs on object or table level. And the locking strategy of Mnesia is fairly easy to reason about. We have tried serializable isolation level on Postgres, and it was unbearable for us, as 15 years worth of Mnesia optimization resulted in crazy many transaction restarts and unacceptable runtimes. So, since serializable isolation level did not work for us, we asked ourselves, how about we lower the isolation level back to something like read committed, the default isolation level, and mimic Mnesia somehow? Can we achieve this? Yes, we can. We can use select for share for read logs, but it turns out that this does not lock non-existent rows, which is something that Mnesia does do. So we need a solution for that. Advisory logs to the rescue. We can take explicit locks for missing rows, and boom, we got ourselves a Postgres, which uses the same locking strategy as Mnesia. So let's look at an example here. We start 2 concurrent transactions, T1 and T2. And for T1, we try to read key 4, which turns out not to exist. In that case, since the for share does not save us, we have to take an explicit lock, and we can do this through a shared advisory lock. Other transactions can take a similar lock, but not an exclusive one, which would allow deleting or updating of this particular key. So at this point, we want to perform an insert of key 4, and hence we try to take an exclusive lock on T2. Since T1 has taken the lock, it will go into a restart loop until T1 is finished. Since T1 is about to write key 4 with value 40, it upgrades its shared advisory lock to an exclusive advisory lock and completes the intended insert and commits the transaction. At this point, T2 is able to grab the exclusive lock on 4, insert into test with the value 42, and commit this transaction. Okay, so now we know how to achieve serializability, but now we have to start to design our database schema. So let's scuba dive into some type theory and learn about how we typed our Mnesia database and created the SQL schema from 15 years worth of data. Quite early on, we had a desire to move away from a key value store which we initially used and kind of explode our records into columns, if you must say. This will start to give us the ability to perform matchbacks in a much more efficient way than what Mnesia provides. And that allows us to shrink the DB size it had due to us not storing large binary blobs, but smaller fields such as integers or booleans. But what should our DB schema look like? Whatever dialyzer tells us, or whatever the type specs of our records tell us. We were, however, facing the problem that our DB is 15 years old, and only in the last few years it started to be enforced by dialyzer. And types in some cases were as wide as any or term. And we wanted to figure out exactly what we were dealing with. So we put together a set of modules which would iterate every record in the DB and determine the smallest common type of each field. So let's take a look at two examples here. So first we have 1, 2, 3 and 1, 2, 3, 4, 5, 6, 7, 8, 9, where the first value is a so-called int 2 and the second one will be an int 4. When we combine the two, the smallest common type where both of them would fit would be an int 4. If we look at a much more complicated scenario, we have here an IP, a tuple, an atom, another array of int 2. We have an int 4, we have a string, we have a binary, and when we combine all of them, the only thing that would fit is a term, which in our case in Postgres would translate to a byte. So now we have types, we have exploded records, but now how to deal with those matchbacks that are floating around in our code base? Let's find out. Mnesia does all of its work on the application side, while we wanted to leverage the DB as much as possible after we kind of exploded our columns. We wanted to be able to push some of the filtering that is done in a matchback into a SQL statement so that the DB could efficiently filter out those results and return us the smallest possible data set that we would have to run our matchback on. So part of the filtering is now pushed to the DB, while part of it is still executed on the application side. We developed a set of modules which does this translation for us as much as possible. And what is required is to send in a matchback together with a prop list of column name and column type, and the library will do the rest for you. So let's take a look at two examples of this transformation. So first here we have a quite simple matchback that matches out that the key is 4 and the IDX is 1. And the resulting SQL query of this is select key IDX value from test I2 where key equals $1 and IDX is $2. The key will be 4, the IDX will be 1. We can also look at a much more complicated matchback, or at least compared to the previous one, where we match out the first name, the last name, an email address, some flags, and a birth date. And we wrap some of this in a when statement, and we do some bitwise AND operations, and we see a resulting SQL query that would be produced. This SQL query would filter essentially everything out that we would need, and on the application side, we wouldn't need to do any filtering at this point.
Yes, so as you could see, getting to Postgres requires a lot of things to be developed. And because of our migration plan, the project will stand or fall, or whether we could make the two databases behave precisely the same. This means testing was a crucial part of our journey. Right from the beginning, we started writing tests that would use our common API and run against both databases to verify they are indeed behaving identically. But we kept running into problems in various edge cases that were not covered by our tests. We realized that we have to ramp up our testing efforts. Property-based tests seem like a perfect fit to our problem. You generate some random input, you run it through both Mnesia and Postgres, then verify you arrive to the same result. So we began writing Postgres tests following this pattern. Proper tests following this pattern. And once started, there was no way back. Currently, we have tests for API compatibility, with a separate set of tests for the matchbacks powering the QLCs, the distribution protocol, the encoding and decoding of types, plus extra tests for verifying the ordering of encoded terms. In Mnesia, you simply use the term ordering of Erlang, and it allows you to compare anything with anything. However, with Postgres and SQL, we get slightly different ordering rules, especially for strings, where locales become important. Then we have tests for the entire type system, because combining types shall be a commutative and associative operation, yet it's very easy to accidentally break these properties. And finally, we have a serializability test suite, which deserves its own slide. The serializability tester generates two transactions, the red and the blue one. It runs one after the other and records the outcome. This is a valid serialization of the transactions. The other valid serialization is if the blue one runs before the red one. The test also knows this outcome. If the transactions would then run in parallel, the result must still be one of the two recorded options. So the test now tries all the possible interleavings of the database operations, using two processes but still running the operations one by one, and verifies the transactions won the deadlock or lead to a third result.
And the time now has come for everybody's favorite, the war story. So like all banks, yes, even this exciting new bank, we have certain batch jobs that run at night. This was a good benchmark for us to try things out on as we introduced network latency to the mix, and things are about to get very interesting, or so we thought. Typically speaking, a set of these batch jobs takes around 1 to 2 hours. And when we started to run our first batch job in a test environment using serializable isolation level, the default one the one that comes with Postgres, we quickly realized we were looking at around 48 hours worth of runtime. And before killing it, we tried to figure out exactly what happened. And luckily, Postgres gives us quite good insights in the type of queries that are executed and how often they are executed. So what happened? We found that we suffered from many reads in tight loops, writes in tight loops, and rereading the same data over and over again, as it's so dirt cheap on Mnesia that nobody cared up until this point. So how did we fix it? We introduced multi-ops to our DB API, and we introduced multi-read, multi-write, multi-delete, which on our Postgres backend could leverage the DB to return, write, or delete many rows with a single network round trip. And for Mnesia, we simply implemented the loop inside our Mnesia backend. We started to pass data down rather than rereading. Yes, this means the increased arity of some of our functions, but we could typically solve this by using a map to just kind of house all of that in one structure. So where are we now? We currently run this set of batch jobs within about 5 to 6 hours, and we've temporarily paused further optimizations as this is good enough for now. We know, however, we can do much more, and we will bring this time down, and we are fairly confident that we will be able to achieve this.
Yes, so we went through the challenges of the migration, and this talk, just like our use of Mnesia, is approaching its end. But we shouldn't say goodbye without confessing how much we will miss Mnesia. Even though our migration strategy was to keep Postgres compatible with Mnesia and avoid changing the business logic, we were still forced to change some common patterns in CRED. Patterns that worked very well with Mnesia, but only with Mnesia. And to be honest, not all of these patterns were nice. Some were downright ugly, and we shall be glad that they are no longer possible. But they will be definitely missed because nothing else, they were so convenient. First thing is relying on the dead cheap dirty reads. You've heard this story already. Dirty reads are essentially just lookups from a hash table, and no select will ever be able to compete with them. Passing around values to be reused later in extra function arguments or in the process dictionary is definitely not fun. With Mnesia, you express the control flow of your transaction and all the searches as familiar Erlang code. You want to know the preferred delivery address of a customer with a given phone number. You have one function already that searches for a customer by a phone number, and one to return the preferred delivery address of a customer. Go on and compose them into a transaction with 2 lines of Erlang code. And you don't have to worry about how the data is actually stored in the database. With Postgres, you could still have the 2 helper functions, but the efficient and idiomatic way would be to write a single select that combines the queries using those helper functions. Suddenly, your 2 lines of Erlang code turned into a complex SQL query that is very much tied to the database schema and would have to be carefully tested independently of your simple helper functions. Mnesia offers strong serializable isolation level, but achieves it using a very simple locking strategy developers can usually reason about correctly. Unexpected transaction results, such as those caused by using adjacent keys concurrently, are rare. People sometimes write code with side effects inside transactions, even though they really shouldn't. And even that won't cause too many problems, because locking and restart semantics are quite intuitive. And finally, apart from the table sizes, there are very few internal limits in Mnesia that may hit you. You can pack thousands of updates, write gigabytes of data within a single transaction, let single objects grow to hundreds of megabytes in size, and Mnesia will just take it all. With other databases, I'm always worried about reaching some non-obvious internal limit. So Mnesia is not the sexiest database in the neighborhood. It's missing a lot of features from its rivals, but it has some secret superpowers too that you won't realize even exist until you try to live without them. With every choice of technology, there comes some trade-offs. How much I value writing all my queries in Erlang? Am I okay with solving all the problems Mnesia left open on my own? I hope we help you to understand the pros and cons of Mnesia a little better, so you can make a more informed decision on whether to go with this piece of technology or not. And remember, if you make a decision today, you may have to come back and revisit it sometime in the future, as your project grows, as your requirements change. Try not to tie yourself too much to any particular technology choice. I'm not saying you should always stick to technology-agnostic abstractions. That won't work either. We created such an abstraction over Mnesia and Postgres, but once the migration is fully completed, we will abandon it, because we want to start using the full power of Postgres.
So if all of this sounds interesting to you, and you'd like to work with us or be involved with similar projects of this magnitude at Klarna, please reach out to us in our virtual booth or reach out to Kalle in the We're Hiring at Tukan and have a chat with us. We'd love to see more of you join us at Klarna. And thank you so much for attending our talk. We greatly appreciate it. Are there any questions?
Yes, thank you very much. This was an amazing presentation and wow, great project. How many years did it take for you to do?
So far, it has taken a little more than a year, and we have probably about 8-9 months left to go.
Cool, cool. All right, we already have a few questions in the Q&A tab. I encourage you to post even more questions. And now I would like to ask Dimitri to unmute himself and maybe turn on his camera and ask his question that he has already posted.
Hello? Can you hear me, I hope?
Yes, we hear you loud and clear.
Cool. So what I wanted to ask was all experience with Mnesia. Could you give some insights on running Mnesia cluster, like for people that didn't do it for 15 years?
I think I will take this. So I have some experience with running Mnesia cluster, but not from Klarna, to be honest, because in Klarna we have this KDB layer that solves the replication between individual Mnesia nodes, basically. And we use that because we wanted to go for consistency in case of network partition instead of availability. We don't want two nodes to start taking purchases at the same time, and because it would be impossible to merge the databases back together after that point. That's not how, the eventual consistency is not something that would work at a bank. But my experience with Mnesia is that it offers you this available and partition tolerant choices. So if you can live with that, then it's good. Then try using it, even in a distributed way. But otherwise, if you can't really accept it, then you have to start enforcing consistency on your own, either the way we did, or by using majority. I don't remember actually, but whether it's a flag on a table or on a per transaction. But I think it's on a table level, so you can tell that updating certain tables, you need the majority of the nodes to be present, and then you get a quorum, and then you will be forced to have a consistent state of the database. But even though, if you have a network split, it's very hard to get the nodes back together. The default strategy, as I mentioned, is just to copy over the entire database, and Figure had an unsplit library that makes it a little bit better and compares tables and only transfers the diff, but it's still a very expensive operation. And in general, I think the rule of thumb is that if you can guarantee that from your Mnesia cluster, there will be always one node that is up and running, and the rest of the nodes will come and join it and then form a big cluster. And sometimes some nodes will leave, but you won't take down the entire cluster completely, ever. Then it's fine. But if you have to take down the entire cluster for whatever reason, due to a bug or due to maintenance, then it gets tricky to start it up again and get to a consistent state. Because the way Mnesia tracks who has the newest version of the data is a bit simplistic. It just knows that which nodes see which other node going down, and you can run into a lot of nasty edge cases with that algorithm, in my experience. Yeah, so I'm actually glad that Klarna wrote a different replication layer to use. This was much better for us than the built-in.
All right.
Thank you.
All right, thank you very much. I would like to ask now Joachim to unmute himself and turn on camera and ask his question if possible.
Yes, hi. I'm just wonder, there are some big databases using Erlang so that you will get the Erlang APIs more or less for free, like Riak. I assume that you have considered them and rejected them.
I can take this one. We have mostly rejected this one because we wanted to go with the kind of the standard that happens at Klarna, which is Postgres. So even though, like, yes, it's being on our radar, we kind of quickly rejected it because it's totally, we would move from a non-standard solution to a non-standard solution, which was kind of one of the big reasons why we wanted to move away from Mnesia in the first place. So that's kind of why.
Yeah, also I would like to add that that we had the strong serializability as a very, very hard requirement, because all our business logic is built on top of that assumption. And we don't have the capacity to review every single use case and all the interactions between all those use cases and say that, okay, we are still fine with some lesser level of isolation, especially not something that Riak offers, which is just eventual consistency. That would mean basically rewriting all the business logic on top of those assumptions.
Right. All right. So now I'd like to ask Mukul, or I'm not sure if I'm pronouncing your name right. Would you mind asking your question?
Yeah. Hi, guys. Yeah, basically my question is, the thing is, we all know that like Mnesia is basically part of the Erlang runtime. So let's say if our latency requirements are very, very low, and so obviously it will be like a better choice, right? I mean, like if the requirements are really, really low and we are building a system in which so that's a requirement. So would you still consider moving away from Mnesia?
Well,
You want to take this one, Dániel?
Yes, I think I can answer it. So I can not really give a good answer to you if you want to use a cluster of Mnesia nodes, because then you are back to the scenario when you have multiple nodes and network latencies between them when you run transactions. But if you have an architecture where you can make sure that there is one node where the database exists and where you want to run the transactions, and the rest of the nodes are maybe just kind of feed replicas, and use Mnesia in this way, then I'm sure that it has a very, very, very big latency benefit over any solution that involves a network hop. And yeah, as we said, that or batch job to initially something like that was estimated 48 hours or something like that, because that's how much it matters if you, for every single write, at a couple of milliseconds instead of being in the microsecond or nanosecond range. The fact that your data lives in the very same operating system level process, that your application code is invaluable. But we are lucky enough that most of our traffic is not that latency sensitive, so we can afford the penalty of one network hop to the database. And I think that unless you are probably in high frequency trading or any other demanding areas, you probably have the budget for that as well, because that's how almost everybody else, apart from Mnesia and maybe SQLite, operates.
Okie doke. Let's take the last question from Håkan. Would you mind unmuting yourself and ask a question? All right, then I can ask the question. So the question is, what Progress client are you using? How did you choose that one? And why did you choose that one?
It was actually a very easy choice for us. We already were using EPGSQL into CRED, so we just continued using that. We didn't even look at other alternatives because we already had it in place for some other use case. So that's the one we were using and the one that we will continue to use.